detecting loop in a linked list. So let's do that. So let's say we are given a linked list which might contain a loop like this. You need to find if there is a loop or not. So a linked list might have a loop, might not have a loop. You need to figure out whether it has a loop or not. So how does a loop work in a linked list? Remember, in a node, you only have one pointer. So it's never possible to have two nodes linked, right? This is never possible that we'll have two nodes linked. So how does a loop work here? Loop will work only if like they are connected in a cycle, like one points to the other points to this, right? That is the only way. It can never happen that it's like this. They both point to the same. So because same nodes two cannot originate, this kind of stuff is never possible, right? So there's a difference between graphs loop and a linked list loop. So those of you who have done graphs would know this is very much a possibility in graph, but it's not possible in linked list. So what we can simply have is a set of all the ones that are visited. So I visit this, I put it in the set. I visit this, put it in the set. So on and so forth. If I ever get a node which is already visited, then I know that it's a loop. So I can have a set or a map kind of thing or any storage which tells me what are the unique elements in it. Okay. So I put this, whichever I'm going through by iterating, I just put it in the set. And I check before putting, have I already seen this element? If yes, then I'll just say it's a loop. Okay, but why, Surya? Why? That's what I'm asking. Why they have to meet? Anyways, I'll prove that. Don't worry about it. So for this, I'll write a quick simple code. We'll simply have a set and I'll say while. So let's say I have my pointer head. While head is not equal to null, you keep on going. So you check first. If your set already contains head, that means it's a loop and you break. Otherwise, you just add current head to the set and move on. Head equal to heads next. Does this make sense? Create a simple set. Whatever node you are visiting, add it to the set. Keep on going. If before adding, you see that it's already there, that means I've already visited this. That means it's a loop and I'll break. Can you tell what's the time and space complexity here? We are taking an extra on space. This is the problem. Time is still on. We are just going over it once. But set space is on, which is the worst. So we need to improve on space and we can do much better than this. That I'll talk about. So again, we use slow and fast pointer approach. And let's see how. So let's say I start two pointers here, slow and fast. And we'll do our general thing. That is fast should move 2 times, slow should move once. So if fast moves 2 times, it reaches here. Slow moves once, it reaches here. Then fast moves twice, it reaches here. Slow moves once, it reaches here. Now can you see that both slow and fast have entered the loop in this particular case? Can I say now they'll never leave the loop? Like if I keep continuing, moving fast, moving slow, moving fast, moving slow, they'll just stay in this loop. They cannot ever go out if it has a loop. Let's look at the distance between slow and fast pointer. Okay. Right now, from one side, the distance is 1, 2, 3, 4, 4 nodes. And from the other side, it's like one node in the middle. Now let's take one more step, move the fast pointer twice and slow pointer once and see what happens. So fast pointer moves twice, 1, 2, and slow pointer moves once here. Now if you see, the distance from the one side between them has become 2, and from the other side it has become 3, right? Why? Because one guy took 2 steps ahead, the other guy took 1 step ahead. So although the direct distance between them has increased, because it's a loop, the other side distance has reduced. Let's extrapolate it. Let's go one more step. What will happen? This will become 3, this will become 2, then this will become 4, this will become 1, then this will become 5, or from one side the distance will become 0 and they have actually met. Can everyone see that? That their distance will be slowly closing off in one direction and they'll have to meet at some point or the other. I'll repeat it quickly. So I'm saying when they entered the loop, this was fast, this was slow. From this side the distance is 1, from this side the distance is 3. Now when this guy takes 2 steps ahead and this guy takes 1 step ahead, the distance increases. That's obviously true, right? If one guy is fast, one guy is slow, the distance increase. But because it's a loop, the other side distance decreases by 1. Because it decreases by 1, we can say it will end up being 0 at the end. So it's not just about one making 2 steps, other making 1 step. Even if one of them was making 3 steps and other was making 2 steps, still they would have met, right? Because the distance will be again closed by 1 unit. If this guy took 3 steps ahead, this guy took just 2 steps ahead, that means still the distance between them will be closing, right? But this cannot be said with 4 and 2. Why? Changes of 2 units. Can you see? Like if the initial distance is, let's say, 1 node and 4 nodes, it will change by 2 units. So from 1 it will go to 3, from 4 it will go to 2. So it might not ever get to 0. Can everyone see that? Yes, if slow is 2, fast is 3, it will work, right? Why it will work? Because the gap difference that happens is of 1. Not exactly jump difference should be 1. Actually, it's related to co-prime. But for that, you need to go a little bit deeper into modular arithmetic. But I'm just saying, if someone asks you, is 2 and 1 the only speeds that are possible? The answer is no. Even when we do 3, 2, 4, 3, 5, 4, these are all also possible. Okay, there are some more, but for that we need to get into detail of modular arithmetic. So we won't do that. But at least this much is very, very easier to spot, right? So basically what you do is you keep on running slow and fast pointer. If they ever meet, that means that there is a loop. Okay, so simple idea.